Students, I welcome you to today's lesson. Today we shall be talking about the laboratory and industrial preparation of ammonia. So quickly, let's look at number one, the laboratory preparation of ammonia. Laboratory preparation of ammonia gas. Okay, let's see the following procedures. Number one, you have the raw materials. That's a mixture of slaked lime and ammonium chloride. Ammonium chloride is heated in a round bottom flat to generate ammonia. So the equation for the reaction is calcium hydroxide, that's the slaked lime, solid, and ammonium chloride solid, okay, to give you aqueous calcium chloride. Steam and ammonia gas. Of course, because steam is produced, so the flask should be kept at a slanting position to prevent steam produced from trickling back into the flask, and that could be dangerous, cracking the flask. So the flask must be kept at a slanting position. All right? Then the gas evolved, the colorless gas. The colorless gas evolved, which is ammonia. Is passed, all right? Is passed through a drying tower, which must contain the drying agent, which is quicklime, that is calcium oxide, to dry the gas. All right? So remember, silica gel can also be used. To dry ammonia gas. All right? So thirdly, the dry gas is then collected by upward delivery method, or by what we call downward displacement of air. All right, because ammonia is lighter or less dense than air. So it is collected by upward delivery. Okay? So remember, you don't dry ammonia gas with tetrazosulfuric acid. Okay? Ammonia gas is not dried. Okay? It's not dried by either H2SO4, either calcium chloride, or phosphorus 5 oxide. Because they will react with the gas, absorbing the gas instead of absorbing water. Okay, let's see the equation. Alright, if you use tetrazosulfate 6 acid to dry aqueous ammonia, to dry ammonia gas, you will end up having ammonium tetraoxosulfate 6. Ammonium tetraoxosulfate 6. And that becomes a waste. Automatically, that becomes a waste. If you use calcium chloride, fused calcium chloride to dry ammonia gas, alright, you will end up having a complex compound, which is calcium chloride dot ammonia. So what it means is that it will absorb ammonia instead of absorbing water. If you use phosphorus 5 oxide to dry ammonia, you will end up, okay, in the presence of 6 moles of ammonia, you will end up in the presence of water, 3 moles of water, you end up having ammonium tetraoxophosphate 5. That will be your, so nitrogen, so make nitrogen 3 times 6, 18, so nitrogen 6, okay. So you have this product. So it's not advisable to dry ammonia with tetrazosulfate 6, calcium chloride, and phosphorus 5 oxide. Straight away, let us look at industrial preparation. Industrial preparation of ammonia. Industrial preparation of ammonia. Alright, the raw materials are dry nitrogen. Dry nitrogen and hydrogen. Of course, nitrogen and hydrogen from liquefied air. Okay. In the ratio of 1:3, respectively. In the ratio of 1:3, respectively, under finely divided ion catalysts acting at a temperature, very high temperature, at a temperature of 450 degrees Celsius to 500 degrees Celsius, and maybe 200, yes, 200 atmosphere, 200 to 250 atmosphere. So the equation for the reaction is nitrogen, 1 volume of nitrogen, and 3 volumes of hydrogen reversibly will give you 2 moles of ammonia gas. Okay? This is the reaction the process we call Haber process. Haber process. So we know it as Haber process. So that is the laboratory preparation and the industrial preparation of ammonia. So next time we'll be looking at properties and uses of ammonia gas. Thank you for watching. See you next time.